precise and comprehensive description of the subatomic world, laying out how everything in the universe, from the smallest particles to the largest structures, is governed by these underlying principles. At its core, the Standard Model describes two categories of particles: fermions and bosons. Fermions are the building blocks of matter, while bosons are responsible for mediating the forces that act between fermions. Fermions are further divided into two groups: quarks and leptons. Quarks are the particles that make up protons and neutrons, which in turn form the nuclei of atoms. Leptons include electrons and neutrinos, which are fundamental particles that don't experience the strong nuclear force. Quarks come in six different types, referred to as flavors: up, down, charm, strange, top, and bottom. A lot of consistency in the naming convention, I know. But each flavor has a different mass and electric charge, with the up quark being lighter and carrying a charge of positive 2/3, and the down quark being slightly heavier with a charge of negative 1/3. Now, protons are composed of two up quarks and one down quark, while neutrons consist of two down quarks and one up quark. These quarks are held together by the strong nuclear force, which is mediated by particles called gluons. Now, leptons, like quarks, also come in six types. The most familiar lepton is the electron, which orbits the nucleus of an atom and is responsible for many of the chemical properties of matter. The electron is accompanied by two heavier cousins, reactions like beta decay, in which a neutron decays into a proton, electron, and neutrino. The strong nuclear force is, as you can imagine, the most powerful of the three forces in the Standard Model, and is responsible for holding quarks together inside protons and neutrons. This force is mediated by gluons, more massless particles that carry the force between quarks. Now, unlike the electromagnetic and weak forces, which diminish as particles move farther apart, the strong force actually becomes stronger as quarks move away from each other. This effect, known as confinement, ensures that quarks are always bound tightly together in groups, forming protons, neutrons, and other composite particles. Now, one of the key concepts in the Standard Model is the idea of symmetry and symmetry breaking. The forces and particles in the universe exhibit a high degree of symmetry, which means that the laws of physics are the same in different situations. But in the early universe, as temperatures cooled, certain symmetries were broken, which led to the differentiation of forces and the emergence of distinct particles. This process of symmetry breaking is essential to understanding why particles have the masses they do and how the universe as we know it came into being. A major component of the Standard Model is the mechanism by which particles acquire mass. Now, this is explained by the existence of a field known as the Higgs field, which permeates all of space. As particles move through this field, they interact with it, and this interaction gives them mass. The more strongly a particle interacts with the Higgs field, the greater its mass. The existence of the Higgs field also implies the existence of a particle associated with it you've probably heard of called the Higgs boson. The discovery of the Higgs boson confirmed a critical piece of the Standard Model as it provided evidence for the mechanism that gives particles their mass. While the Standard Model has been extremely successful in explaining a wide range of phenomena, it's still not without its limitations. One major challenge is that it doesn't include gravity. nature of these phenomena is still unknown. The Standard Model also doesn't explain why there is more matter than antimatter in the universe. You see, in theory, the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, just canceling them out, and left behind only radiation. But the observable universe is composed almost entirely of matter with very little antimatter. This asymmetry between matter and antimatter, known as baryon asymmetry, is not fully understood, as many topics in physics go, and its explanation likely lies beyond the Standard Model. Now, despite these challenges, the Standard Model remains one of the most thoroughly tested theories in science. Its predictions have been confirmed by countless experiments, most notably those conducted at particle accelerators like the Large Hadron Collider. These experiments have allowed scientists to probe the properties of particles with unprecedented precision. So, a lot of unintended alliteration in that. But this confirmed the existence of predicted particles and provided evidence for the mechanisms described by the theory. The Standard Model of particle physics provides an incredibly detailed and precise description of the fundamental particles and forces that make up the universe. It explains how quarks and leptons, the building blocks of matter, interact through the electromagnetic weak and strong forces which are mediated by bosons. The model also explains how particles acquire mass through the Higgs mechanism. But while the Standard Model has been incredibly successful in describing the behavior of particles on the quantum scale, it doesn't include gravity, dark matter, or dark energy, and it doesn't explain the asymmetry between matter and antimatter. As scientists,